Hello students, this is Mr. McAllen and this is part 2 of our video on working with monomials. And here we're going to talk about graphing combinations of monomial functions. So first thing I want to talk about is what we're basically trying to do with these problems is they're asking us to identify based on the parts of these functions how it could look like if we draw a sketch. So you have to think of this as like, we have two functions which are both being put in the same group and they're going to work together to make a picture. And, so we have to identify like, um, think about these functions independently first. So we first think of like x cubed. And x cubed looks like such, and then we look at y equals x. Now, the thing is some of these functions show up at certain values of x better than others. So for example, x cubed shows up or is more prominent in the graph when x gets really, really large. So when x heads towards infinity, you're going to see x cubed being more visible than just plain old x. And the reason for this is if you take any number and if you make that number really, really large, let's say you make x equal to, well, let's just start off, we say x is equal to 1. Both contributions, x cubed and x, will look the same. They'll both be 1. But when x goes to a value, let's say it goes to 10, the x cubed part will look like 1,000, and the x part will just look like 10. So you'll see more of the cubed part than you will of the linear part. Again, if you go to x equals 100, you would see 100 cubed, which would be much, much larger than 100. So, so think about this as we draw the functions, but also we have the tool of Desmos that can really demonstrate this for us as well. So, when we do want to talk about this and identify what's going on, and some problems or some things that we ask you to do in terms of talking about combinations of monomials, what we'll ask you to do is kind of think logically through the problem to figure out what the graph should look like. So the best thing to show you is instead of watching me graph, I think we should just experiment with Desmos to kind of see what happens. So so let's do that. I'll plot x cubed, and you can see the cubic function over here in the window. And then I'm going to add to it the amount of x. So the neat thing about this is you can't really see it, but if I put a parameter in front of x, let's say I just put a parameter b in front of x, and I make that parameter equal to 0, it's as if we don't have a cubic function at all. But when I change b to 1, it's as if you see a linear function here. So I'll draw the y equals x. So you can see that linear function amount. See how it's like the green line and the red line are almost the same when x is really small. Here I'll go to 0 with the b value. I'm dragging back to 0. I mean drag too far. So that's the pure polynomial x cubed. Now I let b go to the value of 1, and you can see how the middle of the function is turning into 1x. Now what do you think would happen if I drove that value to 2? So let's see what happens. If I drive that value to 2, it's as if I have a function of 2x in the middle. So let's check that out. I'll just change the b value here, or the green function, to 2, and you can see how they match. Now if I change b to 3, you could see how the slope of the function in the really low values of x almost looks like the function 3x, thereby kind of demonstrating that the contribution of this overall polynomial, well, the contribution of each part can be seen, and you don't really see too much of x cubed in the beginning. In fact, if I were to just put a parameter in front of that, let's say I put the parameter a there, and I just turn a off, I make a equal to 0 so I don't see it at all, you could see that it's as if it didn't matter if a was there or not for the very early part of the function. But when you zoom out, you could see that the function becomes more like, that red function becomes more like the cubic function. So this is just a demonstration showing how when we add parts to this polynomial, we see different effects. So let's just test that for a moment. Let's say that I put into this function a negative value. I'll put b back in there, and I'm sorry, that should be, let's say that I put a negative x in there, and so you can see how the line is, we have a negative linear function. So if I drive b back to a negative value, I should see that effect on the polynomial, the red polynomial. So let me do that. I'm going to drive or make that -1. So it's, oh, and look what happens. You see how we created early on? The polynomial looks just like -x, but then it breaks away when x cubed term takes over. So what we're hoping, or what I'm hoping you see, is that when you put these two functions together, it's kind of like when you're putting a group of students together to work on a project, and you can see how each term of the polynomial, each monomial term, has some sort of added effect that can be seen in the function when it's added up overall. Hopefully this video has helped you understand how what the effects of adding different monomial functions can have, and you should be able to describe in a logical way what each term should do. Feel free to play around with Desmos, make up your own polynomials, and try this out, and logically go through and think about what's happening as x changes in value. Look forward to hearing your comments, and there's going to be a part 3 video where we talk about more work with polynomials.